Hello everyone, let's go ahead and start with number 17 for the practice test 3. Show how the compound below can be prepared by a route that uses a Claisen condensation. Now the Claisen condensation is that we react two acids, two esters. Now look at this molecule. You have one of the ester part here, and if you count the number of carbons, 1, 2, 3, 4, and the other part also we have 1, 2, 3, 4. So the two esters we identify, and they belong to 4 carbons. So what we can think of is we can break our ester between those 2 carbons. So each piece gets 4 carbons. Now let's identify the ester. So you can see here ester part is CO2CH3. So we're going to condense these two together. 1, 2, 3, 4. COO methyl. Right? And the other one also going to be the same. Oh, like that. And then we are going to do a Claisen condensation between 2 esters. Right? So basically you need a base. So we can use sodium methoxide as the base. So if you use sodium methoxide NaOCH3, basically we try to use the base same as the alkoxide that we find in the ester group. Ester has OCH3, so here also we have OCH3. So the methoxide will grab one of these hydrogens and form a carbanion, which if I draw it, that would look like this. You form negative charge right there. Okay, so once the carbanion is formed, this can go and react with the carbonyl group of the other ester. That would form carbon-oxygen single bond, forming a lone pair on oxygen, having a negative charge as your first step, and then that can go reform the carbonyl group back, leaving the alkoxide group. Now this has to be happened in 2 steps. I showed everything in 1 step, since we explained how the mechanism work in your lecture slides. Okay, so what would you get next? Once this happens, so then you will get this product. OCH3, and over here you will have your carbonyl group and 1, 2, 3. 1, 2, 3. Like that. Okay. So you have our molecule. If you number this 1, 2, 3, 4. 1, 2, 3, 4. And from the other one, if you number this as 1, 2, 3, 4, this would be 1, 2, 3, 4. Okay? Alright. But what we want to make is this compound where we have an alcohol group. But right now what we have is a ketone and an ester. How do we make a ketone, carbonyl group, and alcohol instead of reducing the ester? Which reagent can we use? Lithium aluminum hydride? No. Lithium aluminum hydride will give you all the way both ester and carbonyl group of the ketone reduced. So the sodium borohydride would be the appropriate one. Sodium borohydride only reduce the keto functional group and give you this product that you want. Okay, acetic, the ester group will stay the same, but the ketone will reduce to an alcohol. Okay, That's the number 17. Number 18, draw the product of the following reaction. Again, that looks like a Claisen condensation. Now you know what's happening in Claisen. So the first molecule does not have a alpha hydrogen. So then the second molecule is the one that we should create a carbon ion. So the methoxide is the base, so it will grab the hydrogen from alpha hydrogen from that alpha carbon, and then this would react with this carbonyl group. Carbon oxygen pi bond will break up and form O minus. Once that form, it would reform the carbon oxygen pi bond and leaving this ester group. Okay, remember I'm doing everything in one molecule, but you know how the mechanism work as I explain that in your lecture videos. So this will give you carbonyl group, and then it's this carbon. Okay, we do the connection with this carbon, so that is this CH2, and that has a CH3 group, which is that one, and that has a carbonyl group OCH2CH3. Okay, so that's going to be your product. Got it? Awesome. Okay, number 19, draw the product of the following reaction, and you are adding only one equivalent of this guy. Okay, let's see what's happening over here. For number 19, let's move it up. So again, we are adding a one equivalent of the base, this guy. Now who has an alpha hydrogen? Now first molecule or the second one? The first one has 4 alpha hydrogens. So it could be any of the 4 alpha hydrogens. Ethoxide will come and grab hydrogen from here and create a carbon ion. Once the carbon ion is being formed, this will go and react with this guy and form carbon oxygen. Let me expand this one for you guys since I didn't do it for the first one. Something like this. Okay, and in the next step, O minus will reform the carbon oxygen double bond and then leave this guy. Excuse me, and then the hydrogen that we have here. So that would be the product. Okay, number 20. And number 21, give the systematic name for Cl, CH2, CH2, CONH, CH3. What is the name of that one? Did we do number, did I miss anything? I think I did. Draw the product of the following reaction, number 20. So we have a compound. Okay, how would you get the product of this one? When you heat, what do we get? We have a 1,3 carboxylic acid. Okay, so here in the first position and the third position we have a carbonyl group, 1,3 dicarbonyl compounds. So when you heat, what's going to happen? Something lovely going to happen. So we have a carbonyl group on the third carbon, CH2, and then I'm going to redraw this part putting my OH here and giving carbonyl group aside. And here you have 1, 2, 3, 4, 2, 3, 4. So what's happening here? The thing that is going to happen is called decarboxylation. You are going to remove a carbon dioxide molecule. How is it going to happen? When you have in the first and the third position carbonyl group with the alcohol, these single bonds can rotate and it's going to form a six-membered ring like that. You see, you can have between oxygen and hydrogen can form even hydrogen bond, right? So when this happens, what's going to happen is that you can easily remove a carbon dioxide molecule. Basically, you lose the acidity, you lose the carboxylic nature as carbon dioxide. So what's going to happen? This carbon oxygen pi bond going to form a bond between oxygen and hydrogen. So this bond between the hydrogen and oxygen breaks and form a pi bond. And then the bond, this is a single bond still, okay? And then between the carbon and oxygen, this bond breaks. So when this happens, so this bond breaks, this bond break, this group, what are we going to make from here? This carbon and oxygen going to form a double bond, and you already have the other double bond, and this molecule is your carbon dioxide. It loses a carbon dioxide molecule, but from the other side, what you're going to get is OH enol. Right? Between here and here, you form a double bond. Now, this is the enol, and you guys know enol form can rearrange to keto form, which is this one, this molecule. So once decarboxylation takes place, you will have this as your product. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Correct. So this is the product after the decarboxylation. Okay. Okay, give the systematic name for this molecule given here. How would we name it? It's an amide because it has a, so it has chlorine, CH2, CH2, CO, N, H, CH3. It's an amide because it has a carbonyl and nitrogen. And on the N, nitrogen has a methyl group. So it has a methyl on the nitrogen. So you can say N-methyl. And then the other group, if you count the number of carbons, 1, 2, 3. On the third carbon, there is a chloro group. So you can say 3-chloro, right? Amide. So how many carbons? 1, 2, 3. So then it has to be propane coming propanamide. Propanamide. And we specified that the nitrogen carrying a methyl group, N-methyl. And then in the propane side carbonyl group, there is a chlorine on the third carbon. So 3-chloro propanamide. Okay, that's how you would name that. Number 23. What is the following compound systematic name for number 23? Did we do 22? No, I didn't do 22. Let's do number 22 first. What is the following compound systematic name? That's an alkene. Is it cis or trans? That's a, what is it? Those are your answers. Yeah, here. What is the following compound systematic name? So it's a trans one, correct? And it is an alkene. How would you name this one? What is the longest carbon chain? How many carbons are there? Huh? How many? Okay, let's see. And we also want to make sure okay. Our carbonyl group would take the priority. 1, 2, 3, 4, 5, 6, 7. There are 8 carbons in the longest chain. And then you can see a double bond alkene on the 5th carbon. And this is trans that you guys know, right? So we can say it's a trans molecule. On the 5th carbon there is a alkene. And you can also say oct5-ene, or you can say 5-octenoyl. Octenoyl, why noyl? Because it has a acyl chloride, acyl halide. Acyl halides are named as oil, octenoyl. So this is trans 5 octene oil, octenoyl chloride, since it's a chloride. Trans 5-octenoyl chloride. Octene, in the 5th position you have an ene, that's why it's octenoyl. Or you can say octene, oct5-N oil chloride. But I think 5-octenoyl chloride would be much better. Okay. And then number 23, what is the following compound systematic name? One over here. So we have a carboxylic acid here. And we give the priority to this guy. 1, 2, 3, 4, 5, 6. On the fourth position you have a chloro group. On the 5th position you have a methyl group. So the alphabetically chloro would come first. So there would be 4-chloro, 5-methyl, 6 carbon, right? So then it should be, and it is an carboxylic acid, 6 carbons, hexanoic acid. Hexanoic acid. Okay. And then number 24. How would you name number 24? It's a ester, right? For ester, we normally name the group next to the oxygen and then the ester part as 8. So this one is, there are 3 carbons, isopropyl group. So you can say isopropyl. This is an isopropyl group. Isopropyl 1, 2, 3, 4. There are 4 carbons in the ester group. So then butanoate. It ends in 8. Isopropyl butanoate. Okay, that's the answer for that one. And number 25, draw the product of the following reaction. Now you have an alcohol and a benzoyl chloride. Okay, alcohol and a benzoyl chloride. So basically this is a reaction where we can make an ester. Okay, so what's going to happen here? So the lone pair of the oxygen from the alcohol goes and react with the carbonyl group, opens up the double bond, reform it. Chlorine leaves as a leaving group. So you will have your answer. Oxygen, CO, and then the benzene group. Cyclohexyl benzenoate. It's an ester. Draw the product of the following reaction. So you have a carboxylic acid. You add thionyl chloride. When you add thionyl chloride to carboxylic acid, that would make acid chloride. Just like the previous one, and then you are reacting with alcohol. Okay. First step is that you get COCl, and then you react that with alcohol. Basically similar mechanism like before. Alcohol will react with the carbonyl group and leave chloride, giving you the ester with 1 2 3 1 2 3 like that. Okay, and number 27, draw the product of the following reaction. Now we have a cyclic ester, and then you're going to react it with ethanol and HCl. What's going to happen here? So cyclic ester, it's the OH going to react, lone pair of the oxygen going to attack the carbonyl carbon. So then the pi bond here will open up. So then you will get something like this, O minus, and then this group, and you have oxygen right there. Then you have these lone pairs on this oxygen. So this will reform the carbonyl group and break the bond here. The ring will open up, giving you this molecule, O. And on this carbon you have oxygen. I will number this so you know what's happening. 1 2 3 4 5. 1 2 3. This doesn't look like a bond. 3 4 5. On the fifth carbon you have oxygen. Okay, and this oxygen initially will be negative charge, and then with you can grab a proton and become OH. Okay, 1 2 3 4 5 here. So you will have 1 2 3 4 5 carbon. Yes, this molecule over here you can redraw it to draw it OH, and then it has 5 carbons, 1 2 3 4 5, and then here you have carbonyl group O, this one. So basically you have broken the ring and got your alcohol and ester. Okay, that is the answer for number 27. And number 28, draw the product of the following reaction. Again, this one is hydrolysis of an ester. How do we hydrolyze an ester? Okay, let's see. Number 28. When you heat it up with water in the acidic medium, so this guy, carbonyl group, will first get protonated. So then the water molecule from the medium will come and attack the carbonyl carbon, making this molecule. You have oxygen, OH, and another this molecule, and another water molecule will come. Lone pair can take this hydrogen, giving you neutral molecule. OH. Okay, and in the meantime this oxygen can get protonated. It will grab a proton and become positively charged oxygen with 3 bonds. So one of these oxygen can form a double bond and break the carbon oxygen bond in the ring, making it something like that. OH, OH over here, OH, right? And then another water molecule will come and it's a lone pair right there, and remove this to give you COOH from this side. 1 2 3, 1 2 3, and OH. Yes, so this molecule would be the result. It's the ring opening of a cyclic ester in the presence of acidic medium. Okay, basically in a nutshell what happened in this process, because it's an ester, it's a ester hydrolysis. You break this bond and you give hydrogen to this side and you give OH to this side, carboxylic acid and OH. That is how the ester is being formed between the carboxylic acid and alcohol. So when an ester hydrolyzed, you also form carboxylic acid from one side and then the alcohol from the other side. Basically you're adding a water molecule across the ester carbon oxygen bond. Okay, so number 29, draw the product of the following reaction. Okay, so again we have ester. You are adding sodium hydroxide. So what's happened when you add sodium hydroxide? Again you are breaking the ester bond. You're going to break this bond. You're going to break this bond right there, and you would be adding hydrogen to this side and OH to the carbonyl group. Since you're adding sodium hydroxide in excess, once the acids are being formed, it will not be able to stay as an acid. It can deprotonate to give you the sodium salt. So excess. So let's say before it becomes the sodium salt, what are the two products that we're going to get? So you have your nitro group from this side, and from this side you have OH, and from the other side you will have OH, CH2, CH3. So we are adding sodium hydroxide in excess. So when you add sodium hydroxide in excess, this hydrogen and this hydrogen are very acidic. So they would be removed by the sodium hydroxide and will give you the sodium salt of these two molecules. It would be O minus Na. And then from the other side it would be ONA plus minus the sodium salt of the carboxylic acid. Okay, that's the answer for that. Number 30. Draw the product of the following reaction. Easy one. So you have a bromide and then you are reacting the bromide with cyanide. So it's again in SN2 fashion. Cyanide would substitute for bromide. And then you heat it up. H3O plus and acid, then you heat. What's going to happen? Nitrile will hydrolyze to give you a carboxylic acid. Nitrile group, when you heat it with acid, it will give you a carboxylic acid. 30. Did I get the correct number of carbons? Let's see. 1, 2, 3, 4. 1, 2, 3. Missing a carbon because we added the cyano group. Now it's good. 1, 2, 3. I need to add one more carbon. 1, 2, 3, 4. 1, 2, 3, 4. So for the fourth carbon you added the cyano group. 1, 2, 3, 4. So this cyano group, now this becomes the fifth carbon, become carboxylic acid. So if you want to make a carboxylic acid from a compound that has one more carbon than your original starting material, you can take the halide of that molecule, react with cyano group, cyanide, and then hydrolyze it to carboxylic acid. So initially in our starting material we had 4 carbons. Now our carboxylic acid is 5 carbons. Okay, number 31. Draw the product of the following reaction. Again we have 2 carboxylic acids in the same molecule. That is going to undergo a condensation reaction, intramolecular one. Let's say what's going to happen here. And this one going to form a cyclic anhydride. How do you form this one? You can also refer to the page or the slide 79. Slide 79 of our lecture slides. Slide 79 tells you when you have a carboxylic acid in the same molecule, they condense to form a cyclic anhydride. So this one has 1, 2, 3, 1, 2, 3, 4, 5 carbons. 5 carbons. Okay, so it's an intramolecular anhydride formation. The 5 carbons, 1, 2, 3, 4, 5. 5 carbons. And this one going to be the oxygen. Something like this. So how it's going to happen? It's intramolecular. So one of these oxygen, I'm gonna give you some explanation how this happens. So the oxygen going to react with the carbonyl group. So this will open up, okay, and then it's going to reform the carbonyl group and then leave hydroxide. So you're going to form a bond between oxygen and carbon and form the ring. Okay, you don't need to know how the mechanism, but just know that the product is going to be a cyclic anhydride like that. Okay, number 32. Draw the product of the following reaction. And number 32, you can refer to the slide 82 for this one. I have given the reaction for this one in slide 82. What's happening? So you are going to react this with an amine group. So when you react this with an amine group, what's going to happen? So that your amine is going to look like this: NH, CH3, CH3, and two equivalents of amine. So the amine, the lone pair of the amine, basically going to react with a carbonyl group. Okay, and carbon oxygen bond will open up, this will reform, and it leaves this part. So you will create something like this: CH3CH2 CON CH3CH3, plus from the other side you will have O minus COCH2CH3. Okay, and then you have another equivalent. So this one is the carboxylate anion, and then the cation would be this group NH with CH3CH3, and this would grab a proton and become NH2 plus. So this would be the answer for that. Okay, yes, yeah, so it's just a anhydride being hydrolyzed or reacted with amine to form an amide group, and you can refer to slide 82 to see this reaction. Okay, all right then, so this is the answers explanation for your practice question 3.